Scuba diving is a popular hobby, and for good reason. It gives you access to what seems like an entirely new world, but it can be dangerous. Nitrogen narcosis, for example, is a potentially deadly condition in which divers become susceptible to the narcotic effect of nitrogen at high pressures. If there's one place where you don't want to lose consciousness, it's deep below the surface of the ocean. So how can we combat this potentially deadly condition? Well, to do that, we'll need to learn about gas mixtures. So let's take a look at a simulation of a gas mixture. Here I've got a couple of different gases. It doesn't matter what they are, but you can distinguish them by their color and their size. And this is a simulation of this pair of gases behaving ideally. And so this is analogous to the same simulation that I'd shown before when talking about ideal gases. And the key here is that this is an ideal gas mixture. So both gases behaving ideally. And what does that mean? An ideal gas is one where the molecules, I could use the word particles in this particular case, both are interchangeable in this instance, but these molecules, these particles are not interacting with one another. Now that doesn't mean that they don't come into contact. You can see there are a lot of collisions happening in this vessel right now. But collisions are different than Coulombic interactions or charge-charge interactions. These molecules are not attracted to one another from a distance. They are relatively unaware of each other's existence. They're just flying through space, occasionally colliding, but other than that, nothing much. So this is essentially a system behaving like a bunch of ping pong balls with a lot of energy bouncing back and forth inside. So that's what an ideal gas is, and therefore this is what an ideal gas mixture looks like. But what can we learn about the behavior of this particular gas mixture? Well, like all gases, these are not molecules that are congregating, and so they are filling the entire volume of the space. But both gases in the mixture are filling the entire volume of the space. So when we talk about volume in a gas mixture, really whatever the volume of the container is essentially the volume of both components. In this particular case, both the red component and the blue component are occupying the full volume of the container. So if I wanted to talk about just the blue component, for example, I know that its volume is the full volume of this container. And likewise, that's also true for properties like temperature. So the temperature inside this flask is what it is. We can see at this point it's 300 Kelvin, but regardless, both of those samples, both the blue and the red, they're at that same temperature. Now we'll talk about the relationship between temperature and the kinetic energy of these molecules in just a bit, but for now, the temperature nonetheless is a global descriptor of the conditions inside this vessel. So what is it then that's specific to the blue particles or the red particles? Well, the obvious thing is the amount of particles, right? So I've got a count of particles over here, 50 heavy ones that are blue and 100 light ones that are red. And that is a key descriptor. That is definitely distinguishable between these two types of molecules. So we can have different amounts of the constituent gases in those mixtures. Probably obvious, but important to keep in mind. Now, pressure is another property that we can think of in a little bit more detail. If we realize what pressure is all about, pressure is essentially a measure of the frequency and force of collisions that my molecules have with the side of the container. And if we look at this particular demonstration here, we can see that the number of collisions is definitely different between the red particles and the blue particles. And so what we can infer from this is that the pressure inside this vessel, which is now hovering near 18 atmospheres, is really due to both gases and in a disproportionate way. In other words, if there are more collisions and more forceful collisions from the red particles, then most of the pressure in this vessel is due to those red particles. And a lesser extent of the pressure is due to the blue particles. So the real question is, how can we distinguish between these? How can we attribute a particular amount of the pressure to the red particles and a different amount of that pressure to the blue particles? Well, the answer lies in this count of particles. Notice that there are 50 heavy particles, 100 light particles, for a total of 150. So what does that mean? That means that of the heavy, 50 out of a total of 150 are blue. As a fraction, 50 over 150 is about 33%. In other words, 33% of the particles inside this chamber are the blue ones. And that means that roughly 33% of the collisions that will happen against the side of this container are due to those blue particles. The opposite is also true. There are 100 light particles in this system. 100 out of 150 is about 67%. And I can say that about 67% of the collisions that are happening with the walls of this container are due to those red particles. That allows me to say that 67% of the pressure is due to those red particles. And likewise, 33% of the pressure in this system is due to the blue particles. So these partial pressures due to each component are exactly called that. We call them the partial pressures of this system. So the partial pressure of the blue will be about 33% of the total. The partial pressure of the red will be about 67% of the total. And that is exactly because they make up 33 and 67% respectively of the number of particles in the system. This fraction we're talking about in terms of how much particles, what is the count of the particles relative to the total number, this is something we refer to as a mole fraction. Obviously, if we are specifically referring to the number of moles in this system, that's when we use the phrase mole fraction. And in this simplified simulation, we're just dealing with a specific number, and in fact, a very small number of particles. But in a real gas system, we might have some number of moles of various numbers of components. And so we will have a total number of moles of particles in our system. And that total number of moles determines the total pressure. But the pressure associated with each individual component is really just associated with, what fraction of the total is that component. So let's put some numbers to this. So here's a schematic of that chamber, not drawn particularly well, but I think you get the idea. And what I've done is I've used the same proportion of molecules inside this chamber. So I've got relatively the same number of red to blue, or I guess purple in this particular case. So let's write down some of the things we were talking about. We've got, in this particular case, a volume, V, and that is, of course, the volume of the whole container. We've also got a temperature, T, which is, again, the temperature inside this container. But we've got different amounts. So we've got a number of moles of, in particular, the blue particles, and so I'll indicate that like so. And we have a number of moles, as I said before, of the red particles in this particular system. Now the result is that means that there is a pressure inside this chamber associated specifically with the blue particles, or purple in this particular case, and there is a pressure associated specifically with the red particles. So this seems like a lot to keep track of, but let's just remind ourselves that the total pressure in this system, in other words, the total pressure in this entire chamber, is really just a sum of the partial pressures of each component. Likewise, the total number of moles in this particular sample is also just the total number of moles of each component. And so all of these properties can be interrelated. I have my ideal gas law that can be expressed in terms of the total pressure and total amount, but I also have my ideal gas laws that can be expressed with respect to each individual component. So this allows me to predict exactly what pressure inside this chamber is due to only these purple particles. I just have to know how many moles of them I have. And likewise, I can calculate the pressure in this system, the partial pressure of just the red particles, if I know how many moles of just those red particles there are. So this allows me to express the partial pressures of any component inside this mixture as just a fraction of the total, given the fraction of the total number of moles. Now this has a special name, and we give it the symbol X, and we would say that the mole fraction of some component, let's say the red component, is equal to the number of moles of that red component over the total number of moles. Now, this is precisely how we defined it before. I'm just writing it out for you in mathematical terms. So if I look over here in this chamber and I see that I've got 10 red dots and a total of 15 15 particles in total, then I know that my mole fraction for this particular species is 10 out of a total of 15, which happens to be about 67%, or more literally 0.67. Now, what can I use this for? Well, this is a tool that I can use to predict the pressure of any of these particular components. Suppose I were to tell you that the total pressure in this chamber was 1 atmosphere. If the total pressure in this chamber was 1 atmosphere, I've determined that 67% of that pressure is due to the red dots. And so the pressure due to that particular component is the mole fraction times the total pressure. So let's write that out. The partial pressure corresponding to one particular component is nothing more than the total pressure multiplied by the mole fraction that that particular component occupies. So if we've determined that 67% of our sample is corresponding to the red particles, then that tells us that 67% of the total pressure, whatever that is, and in this case it's 1 atmosphere, is the pressure associated with that particular component. In other words, it's known as the partial pressure. So the partial pressure of our red component is 0.67 atmospheres. And because we know there's only 2 components, the partial pressure of the second component must be 0.33 to add up to the total of 1 atmosphere. So these tools allow us to think about a gas mixture as really just a sum of individual pieces, all behaving ideally. The volume is conserved, the temperature is conserved, and the pressure is really only thought of in terms of relative numbers of collisions of each of those different types of particles. And we can figure out how many types of collisions would be associated with one type of particle by considering what's known as the mole fraction. In other words, what is the proportion of that total system that is due to one particular type of molecule? And that's just expressed as the total number of moles of that molecule over the total number of moles of all molecules. And in this case, that happens to be 67%, but we can have all kinds of different mole fractions. For example, the air that you're breathing right now is about 80% nitrogen. The other 20 is oxygen. Now, give or take a little bit, there are some trace gases in there, but more or less, we've got mostly nitrogen, but certainly some oxygen as well. So we would say that the mole fraction of the air you're breathing is essentially 80% or 0.80 nitrogen. Likewise, it's 20% or 0.20 oxygen. And that mole fraction allows me to determine that if the pressure in the room that we're in right now is about 1 atmospheres, although we could do this with any pressure, if the pressure was about 1 atmospheres, I know that 0.8 of that is due to the nitrogen in the room. And those are some tools that will help us deal with gas mixtures. Let's go back to this simulation of our gas mixtures. You might notice that these light red particles, or red molecules, seem to be moving a lot faster than the heavier blue molecules. And you'd be right, they are moving a lot faster. So we have to think a little bit about what this speed of molecular motion has to do with their properties. This falls under the heading of kinetic molecular theory of gases. The kinetic molecular theory of gases helps us to interpret gas properties as they relate to temperature and the motion of molecules in that system. It consists of a few basic postulates. For one, we imagine gases as consisting of particles, be it atoms or molecules, that are very far apart from each other and don't significantly interact, at least at low pressures and high temperatures. This corresponds to the ideal gas law, of course, and is reasonably represented by the image that you're looking at now. We also presume that the gas particles are constantly moving and collide with one another as well as the walls of the container. Again, like a bunch of ping pong balls contained within a vessel. And finally, we imagine that the average kinetic energy, which is the energy of motion, of these particles is proportional to their temperature. In other words, if we increase the temperature of the system, we increase the average kinetic energy or the motion of these particles. And this is regardless of molecular mass. We say that all gases, regardless of their mass, have the same average kinetic energy at the same temperature. Let's explore that a little bit. I'm going to open up an energy panel here to the left. And what we're looking at now are the speeds of our particles, as well as the kinetic energy of our particles. Now, one thing that we've just pointed out a few moments ago is that it certainly seems as though these red particles are traveling a lot faster, which makes sense given the fact that they're smaller and lighter. The plot that we see here, which is tracking the speed, or at least the average speed of these particles, what we're doing is we're looking at speed along the horizontal axis and number of particles along the vertical. So if we look at the red curve, which is really more of a histogram at this point, we can see that there's a broad distribution of speeds. There are certainly some particles traveling very quickly and others traveling relatively slowly. And I think as we watch these particles move, we can see examples of that. Here is a slow one, and then it quickly changed to being moved to being fast. Again, some slow particles here and faster ones coming around from other directions. And so the distributions, the count of how many molecules are moving at whatever speed, it tends to be quite broad for a light, small gas. Now, contrast that with the purple curve. The purple curve looks quite different. In fact, the vast majority of the purple particles are traveling at slow speeds, and we can see that by inspection. Just looking at this chamber, we can see that there are a lot of slower moving, large purple molecules. And comparatively, very few of the purple molecules are moving with a quick speed. And so this red distribution compared against this purple distribution, I think makes sense based on the picture that we're seeing. And in white is the sum of both. So white is the overall total of the number of particles moving at the various speeds, both slow and fast. So kinetic energy, though, is a separate measure where we are asking how much kinetic energy do these particles have as they move through the system. So kinetic energy is related to both the velocity of the particle, but also the mass of the particle. So if two particles are traveling at the same speed, a more massive particle will have more kinetic energy. So we can have two particles with identical kinetic energy, one moving quickly, one moving slowly, so long as the slow-moving particle is more massive or more heavy. And the kinetic energy plot certainly tells a different story. In other words, the kinetic energy curves for both the purple and the red series of molecules are essentially identical. In other words, we have the same distribution of kinetic energy amongst the red particles as we do amongst the blue particles. And that's because the red particles are lighter, they have to move quicker in order to have the same kinetic energy. And because kinetic energy, as we've said in this model, this kinetic molecular theory of gases, because kinetic energy is related to temperature, which is shown up here, and this entire vessel is at the same temperature, we say that the red particles have the same kinetic energy as the blue particles, so long as the system is at equilibrium. But as you can see, the red particles have to move a lot quicker in order to obtain that particular kinetic energy. This is further highlighted with our clock of average speed up here on the top left. Clearly, my red particles are moving much faster than my blue particles. And this is in an effort, again, to keep the kinetic energy consistent amongst those two types of particles. Now, as the kinetic molecular theory says, if I were to heat up this sample, what I am doing is increasing the average amount of kinetic energy in this system. And this is precisely what we observe in our plot over here to the left of kinetic energy. This plot is now much more broad, so my kinetic energy is spread out over a much higher range. There are particles with very high kinetic energy and much fewer particles with very low kinetic energy because I've increased the total kinetic energy in this system, which is the same as saying that I've increased the temperature of this system. And so this gives us a sense of what temperature really is in the context of an ideal gas. Temperature is a measure of kinetic energy of the particles inside our system. Note that our speed distributions still tell roughly the same story. Again, our red particles are much more broadly distributed in terms of velocities. Some slow ones, some very quick ones, whereas the purple particles are predominantly slow, at least slower than the red. Here's a textbook image to show us essentially this same phenomenon. We are also plotting along the horizontal molecular speed, and then on the vertical here, numbers of molecules. And what we're looking at is a blue curve, which corresponds to a sample of oxygen, specifically at 25 degrees. And then we have a red curve, which is corresponding to that same sample of oxygen, but now much warmer at 1,000 degrees Celsius. And we see these same effects at play. At a lower temperature, we have a more narrow distribution of molecular speeds. So certainly we have some of those molecules moving at 1,000 meters per second, but we have the vast majority moving somewhere closer to 400. But as we heat up the system, same number of particles, now we have a much more broad distribution of speeds. And this higher temperature is indicative of a much higher proportion of molecules moving at much higher speeds. And this helps explain, of course, why pressure increases as we increase temperature. Because as we increase temperature, we increase the velocity of our molecules, therefore they will collide more frequently with the edges of their containers, and the pressure goes up. So in other words, as temperature increases, the distribution of molecular speeds becomes more broad. And we have more molecules that can travel at very high speeds. But of course, that doesn't mean that we don't have any molecules that are still traveling slowly. We do. The distribution is simply more broad at higher temperatures. And it's because of this that we can relate the average kinetic energy of my particles, which I will give the symbol E with a subscript K corresponding to kinetic, and a line over it corresponding to average. This is a common thing to do, to put a bar over a symbol to indicate the average value of that particular quantity. And the average value of kinetic energy of an ideal gas sample can be written as 3/2 R times T. The T should not be surprising here because we know that the average kinetic energy seems to depend on temperature. As we increase temperature, we increase the average kinetic energy of our samples. And this is ultimately how we can determine that average kinetic energy, so long as we know the gas constant. We can also use this logic to define something called the root mean square speed, or the RMS speed of a molecule, which in some sense is, on average, how fast are my molecules traveling. Well, the RMS speed, or root mean square speed, is defined like so. Notice I've got the square, I've got an average, and I've got a square root. So this is where we get the root mean square phrase in this particular expression. I'm using the symbol U here to represent molecular speed, and it's expressed as the square root of 3 times R times T over m, where m is the molecular mass in this particular case. So notice that the molecular mass plays a role in terms of how fast my molecules are moving. This shouldn't be surprising given the slide we just looked at. The simulation clearly indicated that the blue particles, the heavier ones, were moving more slowly, yet still had the same amount of kinetic energy, because mass contributes to kinetic energy. Another way of thinking about that is if you have a large stone that you want to roll down a hill, it takes a lot more energy to move it because it's large. And so as it starts to move, it's carrying a lot more kinetic energy with it than you might think. Whereas a small stone takes comparatively very, very little energy to start moving. So mass makes a difference. And notice, of course, here that it's in the denominator. In other words, if I have a very large mass, my denominator becomes large, which makes my overall RMS speed comparatively slow. Here is another figure that helps us demonstrate this. This is a plot of, again, molecular speed on the horizontal and number of molecules on the vertical. Shown in red is the sample of oxygen that you had just seen on the previous slide at 25 degrees. And comparing that, we are looking at nitrogen, water, and helium. These are gas samples of all of these different molecular substances. And again, they're all at 25 degrees Celsius. So the only difference between all of these samples is, in fact, the chemical nature or molecular mass of each of those molecules. And you can clearly see as the mass changes, in other words, helium being the lightest of all of these molecular species, then water, then nitrogen, then oxygen, the distributions of speeds are very different. And this, again, shouldn't surprise us given what we've seen in the previous simulation. Very small light particles, and note that this nucleus is not shown to scale on this image, but very small particles like helium atoms in a gas sample of helium can have a very broad distribution of speeds and still at the same temperature. So at 25 degrees, the distribution of helium includes molecules that are traveling very, very fast, whereas a sample of water really doesn't include many molecules that are traveling really that fast, even though it's also at 25 degrees. And of course, let's not forget that this is a gas phase water sample. Now, for nitrogen, we can see a similar effect. The distribution of speeds gets more narrow. So again, not as many traveling really quick, and comparatively much more traveling at a slower molecular speed. So this is an illustration of this concept here, where the average or root mean square velocity of these molecules is related to both temperature and molecular mass. Now this brings me to the concept of diffusion and effusion. These are important properties in gas samples, and they can be used to help us learn a lot about the molecular nature of the sample itself. Let me give you an example. Effusion is the process by which a gas evacuates out of a chamber. So I'm going to open up this chamber slightly, and we can see that gas will now leak out of this particular chamber. Now, the rate at which these gas molecules will leak out is dependent upon the velocity, or the average root mean square velocity, that those particles have in the first place. So faster moving gas molecules will effuse out of this chamber at a faster rate than slower moving gas molecules. So in this particular sample, if I want to think about effusion, I think that the particles that are moving quicker should effuse or evacuate out of the chamber quicker than the particles that are moving slower. We can demonstrate this by simply opening up the chamber. Given that the red particles are moving so much faster than the blue particles, even though they have the same average kinetic energy, the expectation is that it is the red particles that should effuse out of this chamber faster than the blue ones. And it doesn't take long for me to leave this chamber open so that I can see that the red particles are now in a far smaller proportion inside this chamber. And we could wait if you wanted to see this whole thing finish, but if I close over the chamber now, I can see that there are relatively far fewer red particles relative to the blue particles now, because they've effused out of this chamber faster. So let's put some numbers to this. We're interested in comparing the rate of effusion of a pair of different gases. So what that really is a relative rate, or a ratio. So if I think about the rate of effusion of gas 1 relative to the rate of effusion of gas 2, that should be related to the relative root mean square velocity of those gases. So using the same notation I used before for root mean square velocity, where this one is specifically corresponding to gas 1 and this one is specifically corresponding to gas 2, I can remind myself what each of those quantities are actually equal to. I know that the root mean square velocity of gas 1 is related to the temperature of the sample and the molar mass of that gas 1. Likewise, the root mean square velocity of gas 2, which is at the same temperature, is related to its molar mass. And given the fact that I've got 3RT both on the top and the bottom of this fraction can be significantly simplified. And we discover that this is actually equated to the ratio of the square roots of the molar mass of gas 2 over the molar mass of gas 1. Note the apparent switch here. Gas 2 is on the top now, and gas 1 is on the bottom. This is because the molar mass of each gas was in the denominator of the fractions that were in the top and the bottom. So 1 over m1 is the same as 1 over m1. And 1 over m2 is just the same as m2. So this relatively complicated expression simplifies to this relatively simple one. And what we discover is that the relative rate of effusion of gas 1 as compared to gas 2 is really just equal to the square roots of their relative masses. So note that if mass 2 is significantly greater than mass 1, this fraction will be a large number. And that tells us that the rate of effusion for gas 1 will be very large. And that's precisely true, isn't it? The bigger the mass, the slower you effused. So this essentially is making a lot of sense at this particular point. Now, let's use this to answer the question that's posed at the top of the slide. We want to compare the relative rates of effusion of hydrogen gas with carbon monoxide gas. So in order to do that, we can tell that we're going to need their molar masses. All right, so the molar mass of a hydrogen atom, as we know, is 1.008 atomic mass units. We've got 2 hydrogen atoms in this particular formula, so our molar mass is, of course, 2.016 atomic mass units. For carbon monoxide, it's a little bit different, of course. Carbon has a molar mass of 12.011 atomic mass units. Oxygen has a molar mass of 15.999 atomic mass units, and adding all that up will give us 28.010 atomic mass units. So now we have our molar masses of each of those constituent components, and they can be plugged in to our equation that we can see up above. And so if we want, we have to call one of them gas 1 and one of them gas 2. Let's suppose our first gas here is gas 1, so hydrogen will be gas 1 in this case, carbon monoxide will be gas 2, and then let's see what we get. So the rate of effusion of H2 as compared to the rate of effusion of carbon monoxide should be equal to the square root of the molar mass of carbon monoxide, which in this case is 28.010 atomic mass units, divided by the square root of the molar mass of my other gas, which is 2.016 atomic mass units. And this ratio of square roots works out to be 3.727. And there are no units to that number because my units would have canceled in this expression. I would have square root of atomic mass units on the top, square root of atomic mass units on the bottom, and therefore no units on my answer. And this makes sense because I'm looking at the relative rates of effusion. And so what does this expression actually tells me? It tells me that the rate of effusion for hydrogen in this sample is 3.7 times faster than the rate of effusion of carbon monoxide. And so this tells me that if I have a chamber and I have it filled with hydrogen gas and I poke a hole in it and allow that gas to evacuate that chamber, it will evacuate 3.7 times faster than it would if I had carbon monoxide in that chamber. And this is actually a valid way to measure the molecular mass of gases. For example, if I put hydrogen in a chamber, poke a hole in it, watch the pressure go down at a certain rate, and keep track of that. And then I have a separate container that I put an unknown gas into, poke a hole into that one, let its pressure drop. I could look at the relative rates of effusion. And if this hydrogen, if I notice that it effused 3.7 times faster than the unknown gas, I can be pretty sure that my unknown gas is carbon monoxide. So this is actually a diagnostic technique, if you will, and it all has to do with the kinetic molecular theory of gases. So what does all of this have to do with keeping you alive when you are scuba diving? Well, let's not forget that as you go down to relatively deep depths, there's a lot of pressure on your body. And so your scuba equipment has to combat that pressure by giving you pressurized gas. And so you have gas being ingested that's at a higher pressure than it would normally be. And because we know that that's a gas mixture, what it means is that the partial pressures of all of the different components inside that gas go up along with it. Now that's a problem in terms of nitrogen. It's a problem in terms of other gases too, but specifically with respect to nitrogen, your body can't handle a partial pressure of nitrogen that's too high. Now everyone's different, but sooner or later, if the partial pressure of nitrogen that you ingest is too high, it has a narcotic effect and can ultimately cause you to go unconscious. So how do we combat that? We still need a high pressure of gas, otherwise our lungs might collapse. So what we do is we supplement that gas with a mixture of helium in a compound called heliox, which has oxygen because of course you need that to survive. But you supplement a lot of the volume of that gas with helium. And so the helium, being relatively inert, doesn't cause that narcotic effect and allows you to bring the partial pressure of nitrogen down in a safe way, allowing us to go to depth and make all sorts of fantastic discoveries.